All right, guys. Linear algebra. Linear algebra, everybody. Anki. Start there. All right. What are the 9 chapters of elementary linear algebra? Well, let me kill these fans. Sequences of linear equations. No, systems of linear equations and matrices, determinants. Euclidean vector spaces, general vector spaces, eigenvalues and eigenvectors. Inner product spaces, diagonalization and quadratic forms. General linear transformations. Numerical systems. I don't know. Numerical methods. Let's go. Let us go. Okay. So what did we read about yesterday? Oh, man. We read about a lot, but not so much. We finished reading the preface. We finished reading the preface. All right. I know we started reading about the proof appendix and the proof appendix of... We're learning about what proofs are, right? They're deductive statements to show the validity of a conclusion. There were 3 points made on proofs. 3 points on proofs. Now I'm forgetting what I wrote down. Dang, dude. Well, we also finished the preface. We finished some author. Right. Resources for students. So we downloaded the app. There's a lot of data files. Dang. Resources for teachers, notes on instruction, collaborators, reviewers. Nothing super important. We went to the appendix. Dang, I'm forgetting quite a lot today, I guess. Right, videos on the website about how to do proofs. All right, let me start at Appendix A. Oh man, this loose leaf's getting ripped. Oh man, it's getting really ripped up. Dang it. Wish I would have got the textbook. I would have if I didn't know what a loose leaf edition was. Linear algebra is more than a collection of problem-solving techniques, right? Linear algebra is more than a collection of problem-solving techniques. Even if you are able to solve all the problems in this textbook, you will still be short of mastery if you do not understand the proofs behind the linear algebra, because in order to apply this linear algebra theory and knowledge in unique applications, creative applications, you need to understand the underlying proofs and theorems. Cool. What is a proof is what we're going to read next. Formality, how to read proofs. All right, yeah, we're going to jump in. I'll be back in a sec. All right, guys, there was a lot in there. Let me retrieve. Okay, so what is a proof? We're pretty solid on proofs. I'm pretty proud of my understanding of proofs. It's basically logical statement that follows logical rules that shows that aims to show the validity or truth of a conclusion based on the logical steps and the premises. Right. So yeah, logical rules. Okay. Formality. So in linear algebra, the proofs don't have to be super formal. They can be in English, like statements, sentences, or they can be written in formal logic. But each step of a logical argument or a proof needs to be justified via referencing a statement that's truth is self-evident, like an axiom, or referencing a statement that has been previously proven. Okay. All right. Then logical form. So typically logical statements will look like H, if H, then C. When it's written symbolically, it's H and then an arrow to C, essentially. And that's read as H implies C. And for this statement to be true, H implies C, every scenario where H is true, C must be true for it to be a true statement. Okay? Anything I'm missing? Right, that's the H is called the hypothesis, the C is called the conclusion. All right. Next up, I will be back in a sec. All right, everybody, cool stuff. I've actually surprised and happy that I know a lot of the stuff already, or I've actually been studying this stuff before on my own and in school. And so we looked at contrapositive. A contrapositive of a statement is basically you take them, the two statements, the hypothesis and the conclusion, and you flip them around and make both negative. So instead of saying if H, then C, you say if not C, then not H. If not C, then not H is the contrapositive of if H, then C. So you flip them and make them both negative. If the original statement is true, then the contrapositive is also always true. Cool to know. The converse, however, when you flip these, so if H, then C, the converse of that statement is if C, then H. This is not always true. It can be true or it can be false. If the converse is true and the original statement is true, well, guess what? That's called equivalent statements, and you can rewrite this symbolically as a double arrow. So H, if and only if C is how you could read the double arrow, or you could read H is equivalent to C. So if and only if, and also equivalent statements refer to a statement that's true, and so is its converse is also true. It can also be written in the form of if, then, and. So if, then two statements with an and, meaning both of those statements have to be true. I think that's everything. Nice. Yeah, I already kind of have learned a bit of this. I'm excited to deepen my knowledge and expand it, because I'm familiar, but I have never really applied this stuff very much. But I really do enjoy logical statements, the if and only if, the and, the or. But yeah, I'm going to keep reading. I got 3 more minutes. I'm going to get through the rest of this second page, and we'll be halfway through Appendix A, and then I'll be back to finish it out. All right, wrapping up today. Basically, the last part of this statement, or this reading today, was about, I think it's called a transitive property, but maybe not. It's basically like when you have one statement in which the conclusion is the hypothesis of the second statement, then you get a third statement for true for free, which is it's the A, if A then B, and B then C, then A then C. The A then C is the free statement that you get. So another true statement. That's it. I'll talk to you guys later.